Okay.
Yeah, I will start recording. Purvita, you don't need to probably, or you do the recording with.
As you wish.
I'm sharing slides.
Yeah, then I'm recording, no problem.
Yeah, okay.
Should I record it or no?
Sorry?
Should I be recording it?
Yes, please do as well. Yeah, if at all there are any issues.
But
Okay.
anyways, we do have YouTube live as well, so we have enough recording from our side.
Okay.
All right. So, yeah, welcome everyone. I'm really happy to have Professor Alena Vencovska. I have learned from her in Manchester. She has held various positions at the University of Manchester during her career, and her research interests include uncertain reasoning, non-standard analysis, alternative set theory, and foundations of mathematics. So today we will hear from her about pure inductive logic. Over to you, Alena.
Okay, thank you. Good afternoon. My name is Alena Vencovska, and I will speak about pure inductive logic. And to start with, I will just talk about some history concerning unary inductive logic, merely trying to convey its motivation and its main achievement, which now dates from almost 100 years ago. And then I'll concentrate on relatively very recent research, which concerns polyadic inductive logic. So next slide. In general, we can say that inductive logic studies to what extent premises entail a conclusion, whilst deductive logic studies whether or not premises entail a conclusion. In the past, probably still it is happening, a lot of effort went to the applied side of this question. So in fact, Rudolf Carnap formulated a program whereby inductive logic should provide foundations for all scientific reasoning. However, that met with considerable difficulties, partly due to the impossibility of spelling out all the relevant knowledge. Was one problem. The other problem was the rejection of the analytic synthetic classification of statement which Carnap assumed. We will avoid this problematics of applied inductive logic and concentrate on the purely theoretical side of the question, which I still think is interesting because it's a study of rationality, and also it might have some importance to artificial intelligence. So next slide. To go quite a long way back, one early approach is due to Wittgenstein, and 8 years before him also Bolzano, called Bolzano-Wittgenstein inductive logic. And you can see what it is about from the table for an example which I put on the slide. So if we were with propositional language, we could consider all truth assignments to propositional variables. Let's just take 2, which are in the first 2 columns. And in the second part, the reddish part, we can see that out of these 4 possibilities, just 3 make A implies B true. And out of these 3, just 1 makes also A true. So both Bolzano and Wittgenstein argued that it means that logically, the extent to which A implies B entails A is just 1/3. And similarly, if we wanted to assert to what extent the combination of A implies B and B implies A, we see in the last greenish part of the table that both premises A implies B and B are true in 2 of the 4 possible cases and A is true in just 1. So logically, the conclusion may be that the extent to which A implies B and B entail A is just half. So next slide. Wittgenstein in Tractatus describes the approach in general in the following phrase, more or less. Assuming propositions are formed from elementary propositions, the degree of probability that a proposition psi gives to another proposition is the ratio of the number of truth assignments to elementary proposition that make them both true to the number of truth assignments to elementary proposition that make psi true. And I want to get the next slide. Okay. Next slide. So both Bolzano and Wittgenstein worked with probability, understood rather intuitively. Since then, it obviously developed a lot, and today probability is understood as a mathematical theory, well-developed mathematical theory, which in general is governed by Kolmogorov axiom. And in this context of probability on languages, if we have a propositional language, and if we denote as L the set of sentences of L, then we say that the function W from the set of sentences of the language to the real interval 0, 1 is a probability function on L if the following 2 conditions hold. Tautologies, logically valid sentences, get value 1. That's condition P1. And the second condition, when we have a pair of sentences which are incompatible, that is not phi and psi is a tautology, they can occur together, then the disjunction get the probability, which is the sum of probabilities of the 2 sentences separately. So these are the Kolmogorov axiom in this setting. And an important thing for the whole subject is that these 2 axioms are enough to guarantee that logically equivalent sentences get the same probability. So everything we do is up to logical equivalence. Probabilities are assigned to sentences up to logical equivalence. Sorry, I'm having problems to get next slide in it was possible before. Yeah, okay, next slide is there. Then we need to say what conditional probability is, and conditional probability is, as usual, probability of phi given psi, the share of phi, so to speak, on the probability of psi. So it's the probability of the conjunction phi and psi over the probability of psi. It's defined provided that the probability of psi is non-zero. And it's not difficult to show that given psi with non-zero probability, the conditional probability given psi is also a probability function. So next slide. Going back to propositional calculus, if we have a general propositional language with m propositional variables, and if we use the notation which we will use throughout, that plus minus p stands for one of p and not p, then we can define W by setting that W of every state description, every combination of plus minus pi, where every pi is represented, to be the same, namely 1 over 2 to the m. You can see this to be this value because there's 2 to the m of them. So if we want to make them all the same, we have to do that because they are also disjoint. So if we define that, we get a probability function on the set of sentences in this propositional language. And it's not difficult to see that the conditional probability of phi given psi, then must be the ratio of the number of truth assignments to the propositional variables that make both phi and psi true to the number of truth assignments to the propositional variables that make psi true. This is true when you consider the disjunctive normal forms theorem. Phi and psi is the disjunction of the state description which implies it, and so is psi. So it comes out like that. So this, in fact, this simple probability function defined like this yields Bolzano-Wittgenstein inductive logic, and the whole theory is quite satisfactory. What is it we are speaking about here? As we said, probability is advanced mathematical theory, and there are many interpretations of it now. So we could be speaking about frequentist probability, physical corresponding to probabilities found in the real world, or we could be speaking about other sort of probabilities up to subjective degrees of belief. What we want to talk about, and what is also Bolzano-Wittgenstein probability best classified as, is logical probability. So what we mean by these values W psi for a sentence psi is that it should correspond to some degree of certainty that psi should logically have, just because of what the sentence is. And the associated conditional probability W phi given psi should correspond to the degree of certainty that psi logically lends to phi. So it should be the probabilities which are derived on the basis of logic. And as we said, we have this Bolzano-Wittgenstein theory, which seems to make reasonable sense, but it makes good sense only when this elementary proposition, which correspond to propositional variables, truly cannot be analyzed any further. If it's a predicate language, then the situation is different. So, for example, assume that L is a predicate language with, well, okay. So let's now consider the predicate logic. And in predicate logic, we will always look at language which will have enough constant symbols. So it will have countably many constant symbols, and it is a convention that they are denoted A1, A2, A3, and so on. These subscripts are meant to carry no information. It's only there because we need countably many of them. So it's just names. And for probabilities on predicate languages, we need one more axiom added to Kolmogorov axiom, which specifies what happens with quantified sentences. So in the predicate context, we say that the function W from set of sentences to the interval 0, 1 again is a probability function under language if the Kolmogorov axiom holds, and moreover something which is called Geifman axiom, and which says that the probability of an existential sentence like there exists x psi x is the limit of probabilities of disjunction of the sentence for more and more constants. So it's, as it is on the slide, it's the limit of W for disjunctions from 1 to n psi ai. So that's the definition of probability functions on predicate languages. And to illustrate what happens, we just consider a predicate language with one unary predicate P. And then the natural idea might be that we take PAI for elementary proposition, and we do the same as Bolzano-Wittgenstein inductive logic suggests. So we give each state descriptions for just m constants, say, the same value. So that would amount to what is on the slide in the middle, plus minus p AI again stands for one of PAI or not PAI. So there's 2 to the m of such sentences, and each get value 1 over m, and we do that for every m. And this again generates a probability function W on the language. But when you think it over, what it yields as a conditional probability function, you find quickly that, for example, the conditional probability of PAN plus 1, given that P holds about a lot of other constants, is still just half. So this probability function yields no induction, allows no learning from experience. It is apparently an unreasonable answer. So next slide. What Rudolf Carnap suggested to do at this stage was that we shouldn't force all state descriptions for the same number of constants to have the same probability. But as is stated in the requirement 1, only state description with equal number of positive occurrences of P should be made equally probable. So it's slightly weaker than what was on the previous slide. But also any of the possible numbers 0, 1 up to n of positive occurrences of n should be equally probable. So next slide. This suggestion, maybe it's easier to see what Carnap was suggesting on an example. So if we consider what he's suggesting for just 3 constants, there's 8 state description. Before we would be suggesting that each should have value 8, but no, every outcome 0, 1, 2, or 3 positive occurrences of P should get the same probability, so quarter. So this slot gets quarter, this slot gets quarter, this slot, this slot. There's no positive occurrence here, and there's only 1 state description like that, so it must get the value quarter. There's 3 with 1 positive occurrence of P, so each gets 1/3 of a quarter, and so on. So that was the Carnap suggestion. And if we do that, we find that the conditional probability we considered before for PAN plus 1, given that another constant satisfy P, is n plus 1 over n plus 2. So as n goes to infinity, it's coming up close to 1. More generally, the conditional probability of PAN plus 1, given a state description in which there are k positive occurrences of P, is k plus 1 over n plus 2. So this is what we get from Carnap's suggestion. This is also known as Laplace's rule of succession. Laplace derived it independently before. And if we consider how Carnap got this answer, which seems more reasonable, we can see that this first requirement is logically justifiable, because it says that each state description for the same number of constants should get the same probability if there are the same number of positive occurrences of P. And if we have a pair of state descriptions for the same number of constants with the same number of positive occurrences of P, then we can just permute these constants and get 1 state description from the other. So by permuting constant, we obtain 1 of these state description from the other. So there is some sort of permutation of the whole framework which maps 1 to the other. And because we wish for a probability function which doesn't assume any interpretation for this constant, such state description should have the same probability. So this requirement seems to be logically justifiable, and when it's generalized to other languages saying basically the same, it is referred to as constant exchangeability principle. and it is one of the cornerstones of inductive logic. It's basically almost always assumed. So next slide.
Just a minute.
Yeah.
I have about actually, what does that negative sign stands for? Is it the non-occurrence or something else? Like in previous two slides, there were plus minus p of. So what does that negative sign stands
Yeah. If you go even further back, I sort of defined it for the propositional. A bit further still. A bit further, maybe, I don't know. Yeah, here. Okay, here it is defined. So plus minus p stands for one of p or not p. So when I write what's on this slide, plus minus p1, plus minus p2, and plus minus pm, it represents 2 to the m possibilities. So in that one line, I am giving values to 2 to the m sentences, which are different, and they differ just whether pi's occur negatively or positively. So this requirement says that w, p1 and p2 and p3 and so on up to pm is 1 over 2 to the m, but also not p1 and p2 and so on. You understand all the combinations of positive or negative. So yes, sorry, it's just once defined on this first slide, and it is used throughout. Plus minus p means that is one of the two possibilities.
Okay, I got it. Thank you so much.
Okay, so we should go back to the slide where I was. Oh, it was requirement 2, I think. Go back.
Here.
Requirement.
Yes.
No, down. Yeah. So when you think what the requirement, the justification of requirement 2 might be, I don't think we can come up with anything much better than principle of indifference. So principle of indifference has been used a lot, and basically it states that if there is no known reason for asserting one rather than another one out of several alternatives, then they should be given equal probability. So accordingly, in this case, one might claim that there is no reason to prefer any of the positive n plus 1 numbers of positive outcomes in state description, and therefore that any of them should get the same probability. Now I said that Laplace derived the same rule of succession as Carnap did on the basis of his requirements 1 and 2, but Laplace's derivation also used principle of indifference. And principle of indifference alone is not a very safe tool. It has been shown to lead to paradoxes in many cases. So the derivation is on the basis of requirement 1 and 2, where one is sort of much safer logically than 2. But the rule of Carnap and independently before him, W.E. Johnson went further and considered another perhaps more logical requirement instead of 2, and that's Johnson's sufficientness principle, and that says that for the simple language we have been considering, because I'm just trying to convey the gist of what had been done. It's all been done for many unary predicates in the language, but just to get the ideas across, I'm using just one. So for the simple language, with one unary predicate, it says that this conditional probability of PAN plus 1 given a state description with k positive occurrences of P should depend only on n, that is how many constant the state description is for, and k, how many of those constants in the state description get P positively, instantiate P positively. So that's Johnson's sufficientness principle. It's some sort of principle of irrelevance. We could argue that it's better justified than the principle of indifference, but not entirely logical principle. Anyway, assuming Johnson sufficientness principle and exchangeability, we can almost determine what the W we are looking for should be, which is sort of identical with saying that we can always determine how inductive inferences should be made when working with unary predicates. As I said, in general, it's done for multiple unary predicates. And what we get is Carnap continuum of inductive methods. And here, just for the mathematical precision, I need to put in a note that, to be precise, really, to get this result, I just mentioned we do need more predicates in the language, not just one unary predicate, but at least two. And whatever I said about positive occurrences P needs to be replaced by occurrences of a particular combination of the plus minus PI. But anyway, in principle, this is what it is about. So the result we get by saying almost determine, I mean that the result we get is not just one probability function, but it's obtained up to a parameter. So next slide. Yeah. So JSP and X are satisfied by a continuum of functions W lambda, where lambda goes from infinity inclusive, from 0 to infinity inclusive. And with one unary predicate, this W lambda gives the following results. The conditional probability of PAN plus 1, given a state description for n constants with k positive occurrences of P, would be k plus lambda over 2 over n plus lambda. So when lambda is 2, this is Laplace's rule of succession. But JSP and EX give a whole continuum of these functions, so lambda can be varied. If it was infinity, then it would be this non-committal function which gives half always. Mm-hmm. Yeah, if it is 0, it only ever gives non-zero probability to state description which are either P's or not P's. So when you consider mathematics, it's certainly intriguing. It's quite a elegant result. The derivation is not 1 or 2 lines. It's quite tricky. However, as I said, Johnson sufficientness principle is not entirely logically convincing, and since Carnap, other rational principles have been formulating, giving other results. So the situation is not entirely clear in the unary case. In the 21st century, polyadic inductive logic had been developed, and one of the hopes is that it could perhaps cast some light retrospectively on unary inductive logic as well, but the whole thing is still being developed. So now I will talk about polyadic inductive logic, and to recall the stage and set it precisely, I've put the definitions again on the slide. So what we are working with is the predicate language now. It's a language without equality. This is important. Actually, it leads to confusion sometimes. So we work without equality. Equality can be added, but it's not in the language to start with. There's no function symbol in the basic setup. Constant symbols are as before. And in the basic setup, there are just finally many predicate or relation symbols. I use predicate or relation symbols synonymously. A probability, a function W from the set of sentences of the language to the real interval 0, 1 is a probability function on L. if Kolmogorov axioms and the Geifman axiom holds, just as we explained them before. So it's the same axiom. So next slide. Conditional probability is defined as before. And the basic question is, if the values of W are to represent logical or rational assignments of Billy value to sentences on the basis of no information, and simultaneously though, W conditioned on psi values should represent assignments of Billy values updated on the basis of psi. What probability function W on L should be chosen? So that's our basic question. Next slide. Yeah. Basic rational principles which are accepted are usually accepted are constant exchangeability, which we already mentioned, which is usually stated in this form, that the probability of a sentence theta doesn't change if we replace the constant symbols appearing in it by other constant symbols from amongst those we have at our disposal. Predicate exchangeability says that the probability of a sentence theta doesn't change if we replace predicate symbols appearing in it by other predicate symbols from the language of the same arity. And strong negation says that probability of a sentence doesn't change if we replace any relation symbol in it by its negation. It's all based on the assumption that W as it is, not condition W, should represent assignments of Billy values to sentences on the basis of no information. So if we don't know what the relation symbols stand for or constants stand for, they should be exchangeable in this sense. So next slide, please. Right. So just to give examples of what I've just said, if we assume that relation symbol PQRST in the language, then exchangeability implies that probability of a sentence like PA2 and QA6 is the same as probability of PA3 and QA10. We can swap constant symbols arbitrarily, obviously replacing distinct ones by distinct ones. Predicate exchangeability implies that probability of RA1 and A2 and QA6 is the same as probability SA1, A2, we replace R by S, and QA6, we can replace just one or both. And SN strong negation implies that probability of RA1, A2 or PA2, A8 is the same as the sentence as it was with R changed to not R. And you can notice that with strong negation, atomic sentences and their negation, like those which are on the slide, any atomic sentence of this form must have a probability half, because both that and its negation get the same probability, and they must have one altogether. Okay, next slide. Yeah, so these principles are usually assumed, and those we considered Carnap functions satisfy them. They do limit the choice of W, but obviously not enough. There's lots of probability functions which satisfy them. And the subject has developed in this century a lot, and many other principles have been proposed and investigated, and they all have some claim to rationality, but they are not all jointly consistent. So the search of some best sub-collection of these principles is still on. And what I will do is that I will describe one principle and its three justifications. Okay, so next slide, please. Right, so to describe my principle, I need a notion of state descriptions. In general, we already considered it for one unary predicate. So a state description for constants A1 up to AN is a sentence of the language which says everything that can be said about these constants using that language, specified in one way or another. So it's usually denoted by a capital Greek letter, say theta A1 up to AN. And it decides all atomic sentences involving these codes. And so I specified it exactly on the slide. So the language has relation symbols R1 up to RK with arities R1 up to RK lowercase respectively. And the description has this form. It's a huge big disjunction, a conjunction over all RS in the language, and also a conjunction of all the possible instantiation of these predicates, either taken positively or negatively, one or the other. So what is on the slide, as I said before, corresponds a great number of sentences, depending on the choice of plus minus being either RS or not RS. Okay, so this is the general form, but fortunately I won't need that. I will work with a simpler language. So next slide, please. This is a rather a slide which would be needed at the end for rather technical point, but I don't think I will go into that. I'll just read what it is. If you have a state description, then replacing constant by variable yields a state formula. And if the state formula for just as many variables as there is the highest arity of a relation symbol in the language, they are called atoms, and they are the building blocks of the formulae of the language from which everything can be built. That's why they are useful. Okay, next slide, please. What I will work with, again, just preferring to give examples that illustrate the results. So it's the language which has just one binary predicate. So for such a language, when this is R, a state description for n constants has the form which is on the slide. So it's a conjunction. We don't need conjunctions over relation symbols because we have just one. It's a conjunction for all ij's between 1 and n of plus minus r aiij. And to be able to talk about this, well, we usually represent a state description by an n times n01 matrix. So it's a matrix with entries either 0 or 1, n times n, to represent these pairs aiij for all the a1 up to an. And there is 1 or 0 in the ith row j's column, depending on whether RAI AJ or not RAI AJ appears in the state description. So on the next slide, there is an example. For 3 constants, the sentence at the top is a state description. You can see it specifies R or not R for all pairs, and it is represented by the matrix below. As you can see, at the first row, that should represent occurrences, instantiations of R with A1 in the first position. So it's no, yes, yes, no, yes, yes. Second row, A2 in the first position, yes, yes, yes. And third row, A3 in the first position, yes, no, yes. So this is the representation which enables us to work with it reasonably. Okay, next slide, please. So we need three sort of notions how we can describe properties of state description for the general predicate language. And it's permuted state description, clone state description, and restrictions of state description. So first of all, a permuted version of a state description is one that looks like if it was obtained from the given state description by permuting the constant. So it could be for other constants, but the point is that it looks like, when represented, it looks like if it was obtained by permuting the constant. So on the left-hand side, in the example, matrix example, there is the matrix represented the state description we had on the previous slide. On swapping A1 and A3, we get a state description represented by the matrix on the right. Swapping two constants actually corresponds to swapping simultaneously the corresponding columns and rows. So permuted state description is one which is obtained by changing the rows of the constant in it. Then, yeah, okay. So next one, please. Then there is the notion of cloned state description. So it's a state description which looks like one obtained by extending the given state description to more constant, but in certain sense trivially. So we make each of the new constant look exactly like one of the original ones. So there is an example again on the board. On the left-hand side, there is the matrix representing the state description we had. And if we add a constant and make it look like A3, we get a state description which is represented by the matrix on the right. So you can see that with respect to any constant which is in it, it behaves the same as the third one. And obviously this bit has to be just the same thing because we can't distinguish the two things, third and fourth constant. So yeah. And finally, the next notion we need for our next definition is that if we have a state description for n constant theta for A1 up to AN, then theta, I should really be saying theta, curly brackets A1, A2 up to AN, square brackets, and then some selected ones, but it is abbreviated like that. So if theta A1 up to AN is a state description and AI1 up to AIK are just some of those constants which feature in it, then theta square brackets AI1 up to AIK denotes the restriction of theta to these constants. So again, example, if theta A1, A2, A3, A4 is represented by the matrix on the left below at the bottom of the slide, then its restriction to first, second, and fourth constant is represented by the matrix on the right. So we just ignore the third one. Okay, next slide, please. And this enables us to define a sort of relation between state description, notion of similarity of state description sharing the same structure as far as structure can be described using the notions we just defined. So we say that two state descriptions for the same number of constants are similar if the following condition is satisfied. Whenever we look at theta and spot some pattern which can be expressed using the notions of permuting, cloning, restricting, then the same thing holds for psi. In other words, wherever theta restricted to some constant is a permuted or cloned version of theta restricted to some other constants, then the same is true about psi, and conversely. So whatever we can express by our notions holds equally on both sides. In that case, we say that the state descriptions are similar, and as I say, it expresses in a certain sense that they have the same structure. So the next slide, please. There is an example, but the example is a bit tricky because it's not so easy to check the two state descriptions are similar. The first two are, And you can check it, for example, well, you will see that the whole thing here, the whole state description here, is in fact a clone version of the first two constants. The third constant clone the second, and that's also the case on the other side. Or you can see that the restriction to the first two constants is the same as the restriction to first and third, which is also the case on the other side, and so on. So if you checked it all, you would come to the conclusion that they are similar. The two state descriptions at the bottom are not similar because, well, the first thing you check is it doesn't work. This thing is just like this thing. It's the same state description, and the whole thing is a clone version of the restriction to the first two constants. But that's not the case here, because the third constant isn't a faithful copy of the second one. So that's some examples. And we come to the first, perhaps not all that convincing formulation of our principle. It is Nathaniel, it has been called under this name Nathaniel invariance principle. It says that similar state descriptions have the same probability. And the reason why this principle should be accepted is basically the principle of indifference, because we want to work with an entirely uninterpreted language. What do we have logically? Logically, for example, we have the structure of state description, and it's an important characteristic. And having the same structure arguably merits having the same probability. However, it turns out that this principle can be justified by other ways, which are perhaps much more convincing. So next slide, please. So for the other justification, we need to step back and look at the fundamental question of pure inductive logic slightly differently. So now imagine an agent who knows that they are in a structure M for the language. And it's a logical agent, it's just sort of Mr. logic. And they don't know what structure they are in, but they still need to assign in some rational way probabilities to all sentences of the language, expressing their belief in the sentence holding in that particular structure. And the question is, in this situation, for a given predicate language L, what probability function should the agent choose? Next slide, please. So to investigate this question somehow, we need to say what it is the agent has at their disposal. Well, they would know about where they can be, so they would know about the set of structures for L with a certain domain. So we assume that we have this set of structures with the same domain, which we take to be the set of constant symbols. So we take these structures to be such that every constant symbol is interpreted as itself, as is often done just to avoid any particular interpretation. So T is the set of structures for L with domain A1, A2, and so on. And for any sentence of the language, we define a subset of this set of structures, a very natural subset, namely the set of structures in which the sentence holds. So the square bracket phi is the set of structures where the sentence holds. So some easy observation about this notion: logically valid sentences are associated with the whole of T, because any logically valid sentence holds in every structure, and contradictions are associated with empty set. And a pair of logically equivalent sentences must define the same subset because they are true in the same structure. So that's the one thing we need. Then, having defined this, curly B is the collection of all such sets for sentences of SL. So it's a collection of all square bracket phi, where phi is from SL. And can easily see that this is an algebra of subsets of the set of structures. And finally, BL is the lot. It's the two-sorted structure consisting of the elements of T, the set of all structures, and of all its subsets which belong to curly B. Okay, next slide, please. And then we can define what is an automorphism of this two-sorted structure. It's just a permutation F of T. It's just a rearrangement of the set of structures, one function from T to T, which, however, also permute B. That means that the function maps every square bracket phi for every sentence phi. It maps the set of those structures which satisfy phi also to the set of structures which satisfy some sentence of the language. So B is preserved by this permutation F of T for it to be an automorphism. To say it in another word, an automorphism is a one function F from T to T, such that for each sentence phi, there is another sentence psi, such that for any structure M satisfies phi if and only if Fm satisfies psi. And conversely, for every psi, there is such phi. So in this sense, if we have an automorphism, every sentence is mapped to another sentence, namely to the sentence which represents the set of structures in the range of the set of structures which satisfy the original sentence. So somewhat abusing the notation, we write F phi also for the psi for which this holds, which is mapped to by F from phi. And so I'm coming, next slide, please. Almost there, my formulation. We would argue that for such automorphism, a sentence and its image would look the same to an agent with only the two-sorted structure, big structure at their disposal. So they should attach the same probability to each of them. So this gives what had been called an invariance principle, the invariance principle of pure inductive logic. But that's quite strong, and when investigated, it turns out that the automorphism of BL can be very wild. And so it had been argued that maybe that we should make this argument involving only a subclass of these automorphisms. Next slide, please. And if we restrict these automorphisms just to those which map sentences which are state descriptions to state descriptions, other state description, whatever, but they do preserve state description. We get what's called permutation invariance principle, and it says that if F is the permutation of our two-sorted structure, that also maps each state description to a state description, and if phi psi are sentences of SL which are mapped to each other, then they should have the same probability. So the argument is just like invariance principle, but it's only taking account of this special automorphism. So this is the second promised equivalent of our principle. And when you think about it, its derivation is based on symmetry, on respected symmetry, which is I believe, much stronger justification than the principle of indifference. So it is a justification of the same principle because they are indifferent, but from a completely different end. Okay, next slide, please. And I will mention the third justification because it's perhaps slightly surprising. It comes from another direction again. I will motivate it for simplicity by an example for a language which either you could think 3 unary predicates or even 3 propositional variables. using what's called Mildred example. This is an example which had been suggested in a completely different context, in fact, to discredit the theory of verisimilitude proposed by Karl Popper. But we won't touch on the direction, but we will just use something which is very well demonstrated by this example. So forget probability for a while and imagine two agents. You can go up. Using three unary predicates, and the narrative behind it was that it's two prisoners sitting in the windowless cell, arguing about whether outside. And one prisoner, Jones, says it's cold, dry, and still outside, which we record as not hot, not rainy, not windy. Smith argues that it's not hot, it's cold, not hot, rainy and windy, and the true state of affairs, in fact, is hot, rainy, and windy. Then it is argued that the prisoners actually could be using a different language, and instead of hot, rainy, and windy, they could be using hot Minnesotan and Arizonan, where Minnesotan would stand for hot and rainy or cold and dry. In other words, hot and only rainy. And Arizonan stands for hot if and only windy, hot and windy, or cold and still. And in that case, translating what's happening above, we find that Jones says not hot, but Minnesota and Arizona. Smith says not hot, not Minnesota, not Arizona. And true state of affairs is hot Minnesota and Arizona. So the import of this question for verisimilitude was that in the first example, Smith is closer, in the second one, naively taken, Jones is closer. Okay, next slide, please. But for us, the information here is that there are many ways in which the same predicates can be used to describe a state of affairs. And here, if the agents wish to use P1, P2, P3, they could mean respectively either hot, rainy, windy, or hot Minnesotan, Arizonan. But that means that the same thing could correspond to P2, Minnesotan, or P1 if and only if P2, hot if and only if rainy. And we are forced to say that if a rational agent is required to choose an initial probability function in absence of any information and with the language entirely uninterpreted, then they should assign all translation of the same sentence the same value. Okay, next slide, please. This is the technical slide I mentioned. I won't go into it. It's just that these notions of translation can be made rigorous. Okay, next slide, please. And the translation invariance principle, as you might be expecting, says that all translations of the same sentence should get the same probability. And this is the promised equivalent to PIP and NIP. Third one with a completely different, from a completely different angle again. So this principle has quite a strong claim. So I'm coming to conclusion. Should take only about 3 minutes to state it. Next slide, please. What is the status of this principle which we talked about? PIP, TIP, NIP, 3 names according to their justification. It is quite a strong principle. It certainly implies predicate exchangeability, strong negation. Doesn't imply X, but X is usually assumed anyway. There is another principle in pure inductive logic, which is earlier and very central, and which is certainly also has a big claim to being accepted, and that's spectrum exchangeability. And that says that the probability of a state description depends only on the multiset of sizes of classes of cloned individuals. Next slide, please. I have put a slide which illustrates it, but it's not important for us at this stage to analyze spectrum exchangeability. Just if you are interested, you can see that these three matrices in the first two, there's clearly just two different types of individuals. So there's 2 and 2, lots of cloned individuals. So whilst the last matrix has every individual, every constant behaves differently. So spectrum exchangeability would mandate the first two having the same probability. Thank you. Next slide. So as I said, this is a principle which had perhaps been investigated most in a pure inductive logic, and it implies PIP. It's even stronger than our principle, the one we described, and a lot of desirable consequences were proved for it. However, it's not well justified. The best justification we can think of is either by bringing some justification from the unary for it by analogy, or using principle of indifference. And why is it that it proves so useful? We can show that probability function satisfying Fx, spectrum exchangeability, can be represented using certain canonical functions which are well understood. So this position pure inductive logic is at now, I would say, is that we would very much like to find similar representation functions for this new principle, which is better justified. But as I say, that's good justification, but we can't prove so many things about it. So please, last slide. Oh, last but one, yeah, maybe conclusion. So in the last 20 years, many principles for pure inductive logic have been formulated and investigated. They all have some rational and justification, but some appear better justified than others, as we have seen. They are not all mutually consistent, and the problem is to select the best consistent collection of principles. Taken together, the principles should be quite strong to determine a probability function or a class of probability functions that could then be declared rational. This has been, in some sense, achieved by arriving at Carnap's continuum of inductive methods, but even so, investigating the general case may still bring new insights for both polyadic and unary. And the very last slide, please. So what we have done is that we concentrated on one principle, pure PIP, TIP, NIP, and we explained the grounds for its acceptance. And it may be that along with X, it will form the nucleus of such a collection, but more needs to be done. Thank you.
Thanks, Alena. This was introduction to a totally new topic for our audience.
Okay, sorry, maybe it was very fast, but
no, I think everything was well written on the slide, so it wasn't too fast.
Yeah, everything is on the slide, basically what I wanted to say. And if anybody wants to contact me with any question, I would be delighted. So my address is...
Any questions from the audience, either in the chat or... I have a question. So you have always said that in the absence of any information about a predicate. So yes, what do you do if you have some information about the predicate?
That's exactly the point. The function should be rational already with the proviso that should I get the information, I will be using the conditional probability. So it should be a function which is chosen to perform rationally when I do get the information. Okay. So for example, when we went through the examples motivating Carnap continuum, we were using exactly this argument. If I was getting the information that P holds for a lot and lot of constants, would it be rational to conclude that the next one, for the next one, P holds only with probability half? We would probably argue that it isn't. We would want the probability function to enable some induction. So that's exactly the heart of the matter. Yeah.
Okay. Thanks.
Thank you.
Any other questions? Okay, so let's thank the speaker.
Thank you.
Thank you, Alena, very much for finding time to speak here.
Okay, thank you.
Yeah, I declare that the seminar is over now.
Okay.
Yes. So, Alena, the YouTube link, we will share that soon with you.
Sorry?
The YouTube link will be shared with you soon.
Okay.
If you want to have the link, I mean, it will be on our website.
Okay, whatever. Yeah. I mean, the slides are more important, I think.
Yeah, slides will also be shared on the website.
Okay.
Yeah.
Thank you so much for such a nice talk.
You're very welcome. Thank you.
It was new to me, but I just liked it. Yeah.
Okay. Thank you.
Yeah.
Right. So I hope to see you around when times are better one day at some real conferences. Okay. Have a nice afternoon. Rest of it.